Hello.
Hi, how are you? Can you hear me?
Hello, yes. Can you hear me?
Great. Sure. I can hear you now.
Okay, nice.
Well, thank you for being here. It's a
Oh,
pleasure
thank you
that
for inviting me.
you accept the invitation. And well, we want to involve our students and our space community here in Mexico to space architecture. So it's a really honor that you accept to be here today.
Thank you very much for the invitation. I'm pleased to be here.
So now I understand that you are in Houston, right?
Yeah, I'm here at Sixa. So I'm
I,
here in the
I
office.
thought that you was in Italy.
No, I was in Italy just for the ESC presenting papers with Sixa, but now I'm back. I'm living in Houston. I'm working here at Sasakawa International Center for Space Architecture at the University of Houston. And so, yes, I'm here. So we have the same time. Should be one also there.
Great. Well, we are trying to create this kind of contest to
Hmm.
involve more people to space architecture. I am an engineer, but I love the architecture because you know that some parts of the architecture and the biomedical engineer have to be related because we have to create some facilities to be more comfortable and to improve the situation in space. So with that said, this time we want to focus this webinar in space architecture, and also we are going to record the meeting because some
Hmm.
of our students are in classes, so we have to
It's
do
fine.
that. So I think you will be speaking in English, but
Yeah.
it's great. I'm going to try to speak sometimes in Spanish because I don't
Yeah.
know if all the people know English.
Yeah.
So I will say something in Spanish now, and later of that you can start with the
Yeah,
webinar.
I have a big presentation with so many slides. I try to merge as much as possible lunar project that I did in my experience as space architect. So feel free to interrupt me if you have some questions, some interest for a specific project because I will go from a project to another. So maybe just
Okay.
I try to focus more on lunar projects because I saw that the challenge is like lunar project.
Sure.
And
Mm-hmm.
one day I will write as well something about space architecture, but I'm an engineer as well. So
Okay.
I think that a space architect don't need to be an architect, but can be also just an engineer or can be both. So it's just, a big branch that can comprehend many type of expertises, I think.
Okay, well, I will speak in Spanish just for a second. Bueno, hola, buenas tardes a todos. Qué bueno que están acá con nosotros. Es una oportunidad bastante interesante. Corrado es ya escuchado, un ingeniero, pero que se enfoca en la arquitectura, porque justo cree que hay muchas ramas que pueden envolverse en el desarrollo de las futuras hábitats que vamos a tener en la Luna. Es importante que si tienen alguna pregunta la pueden ir dejando aquí en la sección de preguntas o en el chat y pues yo se las haré llegar a Corrado. Ustedes creo que lo pueden activar el micrófono por temas, pues ya saben, de seguridad y todo. Entonces lo que vamos a hacer es por el chat. Él tiene bastante expertise en el sector espacial y esperemos que disfruten mucho esta conferencia. Entonces, well, Corrado, we can start. If you want to share the screen, it's time.
Okay, share directly the full screen, so it's easier. You should see presentation. Okay. Tell me if you see the presentation in full screen.
We can see it.
Okay, well, I just give a small introduction on myself. So, well, I'm Corrado Testi. So my previous degree was a master's degree at University of Trento in Italy in architecture engineering. That is like a dual degree in architecture and construction engineering. After that, I moved here at Six in Houston to start the Master of Science in Space Architecture. That, anyways, is the major is astronautical engineer because we are under the department of mechanical engineer and aerospace engineering here at the University of Houston. So I want just to start with something really easy, just to introduce what could be like where come from the passion from space architecture, that not just the hobbies like space launches, but also movies, books, comics, video games. So I think that everything is useful to feed your mind, to have the curiosity to explore this field. So I want to start with my first real approach to the university with space architecture. That was my first master thesis at the University of Trento. So, as I said, was an university of engineers, and in Italy, space architecture as is not known like here in US. So was a little bit difficult to start this type of topic in a university of civil engineer, basically environmental engineer and architecture, but I insisted, and I had two fantastic supervisors on master thesis. There was Professor Giovanna Massari and Professor Diego Missironi, and as a co-supervisor, the space architect Vittorio Netti. So my first master thesis was creating and study the design of the first human outpost on the lunar surface. So just what I did was try to introduce the field of space architecture also to people that don't know really well the field. So try to give a really broad idea what space architecture is, but obviously we have the big umbrella of architecture, and inside we can define the architecture of extreme environment like a part of architecture, obviously, and inside architecture in extreme environment we can see the space architecture. Obviously we have some examples and some research, so we can define the space architecture, obviously the most known part of the space architecture is the International Space Station, but also the other commercial space station that soon will be on orbit, like Orbital Reef or Blue Origin Aerospace, but also the Axiom one and many others like VAST or other companies that are developing their own space stations. But also, obviously, we are talking about space architecture when we are thinking to create a sort of to establish a sort of colonies in a different celestial body, like it could be Moon or Mars or others, obviously, if you see more far in the time. But obviously, we can consider space architecture also the outer space. So could be like asteroids, could be like the deep space, but also could be like a transfer vehicle, for example, from Earth to Mars. Because, for reach Mars, everyone is saying, well, we will go to Mars, but obviously you need to consider how you will go to Mars. That will be 4 or 6 months of travel. And also, obviously, that will be part of the design. So, space architecture obviously involves human factors, and but not only that, because if you're building something on space, you have to know pretty well all the systems, the technologies that are related to space, so the launchers, the vehicles, the landers, so all the system, and you need to integrate them. So if you're building a base on the moon, you can't just create, a big tower on the moon. You have to consider also the constraints of the mass, the volume, how you launch it, all the constant operation, the orbital constant operation that you need to plan before reaching the lunar surface. And also, once you reach the lunar surface, you need to plan also how you deploy your module from the lander, how you transport from the landing site to the base site, how you build, how you stack together the module. So every part is important, in the space architecture. So not just basically design the interiors, but also to understand how to build stuff. So when I did my master thesis, I tried to study. So a big part of this master thesis is the research about the lunar environment. So understanding how it is the day and the night on the moon. That is pretty different from Earth. We have 14 days of night and 14 days of light in the equatorial area of the moon. Obviously, we need to consider also the inclination of the plan of the moon with the ecliptical of the sun, because this is more important. For example, if we are considering to build a base on the South Pole on the moon, for example, where obviously we have a completely different view of the sun that is basically always at the horizon. So always the lit part and the shaded part are an important part of the environment of the lunar south pole. You need to consider the gravity and many other features. Also, you need to consider the terrain that this is what we know basically from the Apollo mission. So they are like odometers and the estimation of the relative density of the terrain based on the prints, the footprints, and the prints of the landers. If we are considering that, we can estimate that has a good resistance, the terrain of the moon, if you are considering the equatorial area, the Apollo area of landings. But obviously, we need to consider that now we are planning to deliver to the moon more tons, and the lunar module was around 15 tons. So if we are planning to land Starship, obviously, will be a different game. As I said, we need to consider on the moon what are the risks, because the moon is a really harsh environment. There is almost not atmosphere or really, really thin atmosphere. The gravity reduced 6 times in comparison to the Earth gravity. There are meteoroids shower on the moon, so you have to protect from this type of hazard your habitats. You need to consider also the moonquakes, so the seismic activity on the moon that has really low intensity in comparison with Earth. But obviously, you have to consider that there are really long periods, and the biggest recorded moonquakes on the moon are for meteoroids impacts or modules of rocket that impacted on the moon. And obviously, the radiation and the extreme temperatures. For what was my project, that was my first project of space architecture. The concept was like the idea to deliver a sort of seed on the moon and let it bloom. So I designed this sort of a rigid habitat stuck together with an inflatable habitat on the top. So we are talking for inflatable habitat like the Sierra Space Research that they are doing the Life module, if you know those type of technology advancement. The rocket used was Starship, and the inspiration was related to a really old type of architecture that was based in Italy, in Sardinia, that are these nuraghe. So the idea around that was like to use the 3D printing in a long-term timeline to the aim to protect those modules for a long-term period. So the idea was like to use binder jetting printers. So in this way, we can print directly with the resources that we have on the moon. So we are talking about the regolith. Print these bricks, and you see inside was done a little bit of research how to reduce the material that you use. So the idea was like to have a sort of honeycomb interior, so you reduce a lot of material and try to make a rigid part on the exterior of these bricks. So you are like simulating the Whipple shield. If you don't know what is the Whipple shield, it's basically a sort of layers that how they build the protection, for example, in the module on the International Space Station to avoid possible debris impacts. And so the idea was like to create a lunar nuraghe. So nuraghe is like the architecture used in Sardinia in the Neolithic area, just stacking bricks. So was done also, as I said, was an engineering university. So was done also the structural analysis of the modules. And was done also the study. This is like a short trailer of the project. It was like pretty huge. It was like 250 pages, but I will just do, otherwise there is no time. But what studies also the psychological aspect. So obviously on the moon, as we said, there are long periods of dark. And this can impact really, can have a negative impact on the mind of the astronaut because they are used to have a cycle, the circadian rhythm. And so we are trying to emulate the sort of rhythm that you have on Earth, on the moon, using a sort of changing of lights inside the module. So trying to use warmer lights, for example, for the morning and the noon, for example, and going approaching to the evening and the night with more cold lights like the sun and the purple that you see on the images. So this was like a final render of what could be this base on a terrain that was extrapolated from the data of the Lunar Reconnaissance Orbit, that is a satellite around the moon, where we have all the data, the altimeter, the data of the height of every point on the moon. So after that, my choice was like to try to understand how to pursue this career. So try to become a space architect, a certified space architect. So my idea was like, well, I evaluate many type of options, but I choose to come here in Houston to start this Master of Science. I see that there is something in chat. No, okay. I go ahead. Okay, so I started SIGSA. So I will propose this. That was the first project that started here at SIGSA. Was a project that was in collaboration with SIGSA and the Marshall Space Flight Center. And about this project, that was we had also a patch was called Laser. So the idea was like to create a lunar approach. It was standardized, expandable, reusable, and relocatable. And there are 3 papers that I presented in 3 different conferences. One was in Louisville, in Kentucky, the ISIS last July. The other one was in Las Vegas, and the other one was in Milano the last October. And you can find online these papers. So this was basically the methodology, decision tree that we used for develop these projects. So the idea was like to start with the vision, mission, goal, objectives, define the requirements that partially were defined by the NASA Martian Space Flight Center, and define the function that was starting with the test in the early phases, continue the legacy of the Apollo mission, so starting with geological science and go ahead with the SRU, biological science, and others. And obviously rising complexity, the function rising with the timeline and the phases. So the requirements were defined for the environment, the mass, the volume, the energy, and the crew. So we enlightened the CONOPS, that is the paper that we presented at ISIS in Louisville, the concept of design, and at the end, after defining the capabilities, the mass estimation, the final evaluation of the project was a virtual reality evaluation, and also for that there is a paper that we presented at the last conference at us, and me and my co-authors. So the idea was like to figure out what NASA is planning for the next Artemis mission. So this is the last roadmap of NASA. So we already have Artemis 1. In 2025 is planned Artemis 2. Obviously, the idea is that we need to start to deliver our first surface habitat, thinking that all these Artemis missions were successful, and so we already have some asset on the lunar surface. So the assets that are already on the lunar surface, and we use that as assumption before to develop our project, was the power grid, obviously. So we are talking about solar vertical panels and nuclear energy. Obviously, we are talking about a lunar base on the south pole of the moon. The LSMS crane, that is an asset that is already tested, a sort of lightweight crane tested from NASA. The Athlete, that is another robotic transportation system developed during the Constellation program by NASA. The Lunar Terrain Vehicle, that we got inspiration about the Venturi Astrolab, that now is one of the contractor of NASA, one of the 3 lunar terrain vehicles selected. Obviously, we are thinking about a Raster, but not just like that, but all the robotics around the ESRU exploration. The pressurized rover that we modified, the NASA one, and the Skyflower lander that obviously here was just a conceptual lander that now I'm developing with my actual research more in deep. So these are the habitation elements that we developed during this project. So the idea was like to have a surface vertical habitat that was an habitat that hosts for astronauts. This is the node. The node is a part of this base that is attached under the surface vertical habitat with different interfaces that could be just 2, 3, or 4. You see these angles define the angle between one interface and another can be used to develop the base in different direction. And also this in the second phase is used as a sort of safe haven of protection for radiation events, so like solar phase. So the idea was like to add an additional internal layer enriched by hydrogen. That is the best element to protect astronauts from radiation events. And there are many radiation events, not just solar events, but also cosmic radiation. There are many, but obviously one of the most impactful could be like a solar flare, for example. We are not anymore protected by the magnetic field of Earth on the moon, and so it could be a big problem if the astronauts are in the habitat and are not protected from radiation. Another module was the horizontal type 1. So the idea was like to have a deployable module that start like deployed linearly. So it start like packed with 5 meters, and after you deploy and you inflate it. So you deploy with the use of the lunar terrain vehicle. And another module was the horizontal type 2 that was that it does a lateral expansion. So all these modules are hybrid modules. So half rigid and half inflated. So let's define a little better this module. So this is the surface vertical habitat. As you see, there are those huge landing legs. I will explain better later, but it's a feature that can solve a lot of problems from our research. As you see, there is a first floor that is the rigid part of the module. So hypothetically, this module can also split in 2 different modules, and the second one, the class 2, can be packed later. And if you see the interior and from this elevation and the section on the right, you see that our idea was like to dock the pressurized rover from the bottom. That's the reason why these landing legs that rise for 4 meters the module. So you can allow a vertical connection instead a lateral one. That could be more problematic. And also how we organize the space internally. Well, we got inspiration from the old space station like the Freedom and the Skylab, but also the International Space Station. So our idea was like to separate as much as possible the most active and dirty area that we defined as the rigid part, because there is the airlock. So obviously the dust is a huge problem on the moon, and you want to keep the astronaut far from the dust as much as possible. Also, we put the ECLES system, that is the life support system, inside this module. And also we added the hygiene module that is really smelly. So we decided to separate as much as possible from the 3rd floor, that is like the private space for the astronaut, where there are the private rooms and the galley, and we insert a buffer zone in the middle that is like the control room of the habitat and the VA. So let's see now better in detail the node I already explained before. We had also this sort of attachment that can solve problem with tolerance. The attachment, as I said, is simple because it's not inflated when you attach, but you inflate it later. Can solve problem about the slope, because obviously you put 2 modules, but the surface on the moon is not flat like you see in many renders about the project on the moon, but there are a lot of problems. And also there is the radiation shell inside, as I said before, and the expansion in multiple directions. Obviously, the idea is like we start with just 2 interfaces, because also adding interfaces in a module, it means that you are raising mass and you are adding more complexity, so more failure points. So the idea is like we raise the number of interfaces with the functions and with obviously the know-how that we have on established lunar base. The horizontal type 1, as I said, is a really narrow module. So the idea was like to expand it laterally. And the idea is like to use this module to connect different clusters of surface vertical habitat. The idea that we had inside is like is a really narrow module. So we studied a lot how to put these racks at the interior. And we find a solution that was studied by Sandra Happler and Marsburger with the Flex Hub. That was a study done in collaboration with ESA, the European Space Station, the European Space Company. And so the idea was like to put the racks in those rails. So in this idea, you can move those racks, you can create niche work places. You can also add different things. You see in this render, there are like 3D printers. There are like cultivation racks. So you have a possibility to adapt your functions at this model as much as possible. For the other module is not really defined, but the idea is like we have more space, and so we should use this module for the laboratories. So each one could be a different laboratory. We can put a lot of things inside, and so we have like a relatively low mass, but we gain a lot of volume. So the landing legs, let's start to define a little bit those landing legs. So we got inspiration for landing a module directly from the bottom of a lander. So we don't want to lose completely the lander. So the idea was like to adapt a sort of sky crane, like the Martian sky crane used for Perseverance, but obviously adapted for bigger mass, like a module like this. Obviously in this image is landed like this, but the inflatable would be for sure not inflated during the landing phase. And obviously this lander is not dimensioned for now. The inspiration of the landing legs is inspired by the landing legs of the Falcon 9. So the idea was like to readapt the cinematic chain of the landing legs of the Falcon 9 to this design. And so the idea is after you land, you have crash core integrated to the landing legs. And so the shock get absorbed by these elements, and after you don't have to land it again. So also after remains just legs for stabilization. For the other modules, the idea was like that we can land also with different type of landing system, also ordinary landing system. So we provide normal landing legs, so normal, not landing legs, but just landing legs used for stabilize the module. So the idea was like to solve the problem of the moonquakes, the vibration, possible collision, and impacts. So the idea was like to integrate inside the feet of these legs a triple friction pendulum bearing. So the idea is inspiring this type of technology used in Japan for the foundation to this system. Obviously, in a smaller version of that. And obviously you need in some way to print the foot to stabilize once you place the module. So you need to attach the bottom part of the foot to the lunar terrain. In this way, all the base, there is less vibration. If there is a moonquake or sort of vibration, you risk less to break, for example, the attachment between different touches, or I don't know, different type of problem that can occur in these situations. Obviously, we get inspiration for the ECLES system, so the life support system from the ISS, and we try to figure out how to integrate this system in our modules. So this is an early phase, and you see that the idea was like to use redundancy as much as possible, in particular for the life support system. So provide a secondary ECLES system in case the one fails, so you have at least time to evacuate the astronauts from the base. So the evolution phases that we study. So we start with the phase 1 that we just have the vertical surface habitat landed in that place and the pressurized rover. So we just have a short mission after Artemis 7 or 8 for 4 astronauts. So we are talking about 7 days of mission. After you start to add modules, so like we are talking about, for example, adding the node and adding, for example, an horizontal type 2, you can land the pressurized rover on the side, and in this way you still have room for 4 astronauts, but you are expanding the volume. So maybe you can also expand, for example, the duration of the mission. You can start with mission of 14 days. After in the phase 3, you can start to add more vertical surface habitats, so you can add another crew, and obviously you can add still more pieces until you reach the idea in our definition of phases, like phase 4, to have in a base 12 astronauts, so 3 crews of 4 astronauts, that everyone is in each cluster of surface vertical habitat. We also studied the idea of like protect this habitat in a really long term, but it's not really deeply studied this part. So for the orbital columns, obviously we base our maneuver for the Artemis 3 mission. So the idea was like to use as an asset the gateway. So we reach the gateway, and after that we start the maneuver from the near rectilinear orbit to the surface on the South Pole. So we did a sort of estimation of mass of those modules that is obviously is not really defined, but can be improved. This is a really overestimated mass that obviously will be reduced after better estimation and optimization of the design of the modules. And obviously we decided which launcher we can use for each module. Obviously the more constraints that we have are for the surface habitat. It is obviously the most heavy in terms of mass. We studied the orbital CONOPS that, as I said, the idea was like to use this sort of system. So we start from the gateway, we deliver the module in low lunar orbit. We land directly the vertical habitat of the moon, and we wanted to use this sort of landing system as a reusable system. So with this system, we can come back to the lunar gateway, we can refuel it, and we can land another module. So this process can be used many times to define your concept operation of evolution for the lunar base. Obviously, considering in a long term of evolution of the base, we were considering to readapt this system also as an hopper. So the idea was like to take modules or other assets from a point A to the lunar surface and redeploy from a point B to the lunar surface. Obviously, here stay in a really concept way of the study of this landing system. Now, as said, I'm studying more in deeply this system. This is obviously completely detached from this project, so it's just related to the landing system. And obviously, before landing on the moon, we need to consider the study, the precision of the landing area. And this could be like a small simulation. How can be this landing system, obviously with a really reduced amount of mass. For now, the study is just for 2 tons, so we are pretty far to the 20-25 tons of the other modules. But here is shown how could work this sort of lunar skycrane that obviously has many advantages in terms of plume surface interaction. Instead of a conventional lander, you can deploy a payload in more areas than a conventional lander because you have less limitation about the slope. And obviously, the reusability of the system is a really good advantage. You can refuel it in orbit. So this is another video of the deployment. You see this is like the readaptation, obviously, of the Martian skycrane for lunar purposes that I'm studying this directly from another project. So let's go ahead and see about the laser project, the surface concept operation. I will try to go faster, otherwise I don't know if I stay on time. I will go faster. I just want to show you how it's important, for example, also for this problem of the surface plume interaction, because once we land on the moon, we have this big problem that we risk to blast a lot of regolith around the landing area, also for 1 kilometer, and so we risk to destroy all the assets that are already on the moon. So that's the reason why from our project we decided to select additional landing site for each additional landing. And also is important for the moon also in geopolitical talks, because imagine if US or another nation land pretty closely to US or another nation, and you risk to destroy the other nation assets. So it's like a declaration of war, but also for your assets. So you don't want to destroy what you already landed on the moon. So you need to take care about this. So our idea was like we land before the first surface habitat, we land the furniture inside, the consumables, and what you need to put inside the module. So using in an autonomous way, the pressure rover, you can dock from the bottom, and with a crane, you can already put inside the modules or what you need. So once you land the astronaut, the first astronaut on the moon, and you deliver this astronaut to the base with the pressure rover, the lunar terrain vehicle, they already find everything what they need inside the module, and they just need to fix it. But the eclipse system, for example, is already there, and all the furniture are already there. So after you can land the other modules, for example, you can install it. You can, for example, was a constant operation using the SMS crane to deliver a module in collaboration with the lunar terrain vehicles, for example, for a correct deployment. And obviously, was how we installed the module. And obviously, this is the usage of the athlete. That is a well-known asset, but you can, for example, attach a module. You can detach in two pieces the athlete. And in this way, you can directly attach in the right position, facing a lot of problems with the lunar terrain that you see in the image here on the right and the bottom. So after that, the idea was like to grow the base more and more. And after that, the idea was like in the future, we can also relocate some of those modules and we can explore other areas of the moon. So we studied the sites. Obviously, these are the landing sites selected for the Artemis 3 that now are already updated. There are less of these sites. They are more close to the Earth side of the moon. So the most important part that we studied for select our site was the lunar illumination for exploit as much as possible the solar light, and also the slope. So a sort of mobility with different points, like you see here, the connecting ridge area, the Shackleton rim area, and the permanent shadow region area close to those area. We are not talking about the Shackleton crater because obviously it's really deep and it's really difficult for the yearly mission to reach it. But is basically how we studied the development of our base in those different areas. So this is the connecting ridge area, this is the Shackleton rim area, and this is the permanent shadow region. Obviously, what changes is a lot of factors. Also, the area that you have available to build the base, because obviously in the Shackleton rim there are really narrow spaces, so it's not flat like you see, for example, in the SOM project for the lunar village. But also the usage of nuclear energy and solar energy is really different. So now I want to introduce the final part of this project. That was the evaluation of using the virtual reality, in general, extended reality for this project that we did here in the XR lab at SIXA. That is the lab where we are developing many type of evaluation for operation and rovers and lunar habitats and whatever. And so let's try to explain better and try to go faster the extended reality umbrella that comprehend the virtual reality, the mixed reality, and the augmented reality. So if we see what is in the real life, basically we have is the physical environment around us. If we see what is the augmented reality is the real world environment that we have around us, but we superimpose digital object. For the mixed reality is the real world environment with superimposed digital object, but you can interact with this digital object. Instead, the virtual reality is a complete digital environment. I show here some example of augmented reality. For example, you see in the industry or technician using like pad to superimpose those objects, for example, for a maintenance of a machinery, but also mixed reality. You see here on the top how they built the Orion spacecraft for Artemis, for example. So it was like a low fidelity mock-up with superimposed the digital model, and virtual reality like evaluation in a complete environment, like you see lunar habitats like our laser project, but also rovers, but also other type of operations. So this is the VR lab that we are using at SIGSA. Obviously, we have big advantages to use this type of technologies for evaluation because you don't have to build a physical mockup that is really expensive and time demanding, but you can iterate using this type of technology many times, and you can come back using a human perspective to evaluate your design. So we are doing here surface testing and microgravity testing with the usage of a crane, for example, to reduce the weight of your body while you're doing the VR evaluation. So this is the framework that we use for a VR evaluation of an habitat. I will try to go faster, and the final outcome should be an AR evaluation. So we start with VR, that is a really low fidelity, transition to mixed reality, and at the end will be the augmented reality. So I want to show you faster, for example, how it is the first evaluation that we did for this habitat. So you see here how we did the evaluation using the VR headsets for our habitat. You see on the top, this video is a really low fidelity first evaluation of the volume of those habitats we designed. For example, you see here that the rack system is completely different for what we designed at the end. So from this evaluation, we understood that this system couldn't work, so we redesigned. And you see here a final evaluation with the virtual reality without any type of interaction, but just to understand how work this environment once designed. After that, we added collisions and we added interaction. So we start to do operation with our habitats, and we integrated with Luna Terrain, that is the NASA exhaust, where we have with SIGSA collaboration with Buendea, and integrating the biosensor, so monitoring the how your body answer to this operation. So, for example, the heartbeat, your movement of the hands, if you are sweating or not. So we have a framework that we are developing here, SIGSA, to evaluate this type of operations. So for this additional operation, we wear this suit that we designed here at SIGSA. So for the third subject, we had problem to wearing the suit because our co-author is too big to wear it. But this was like basically the evaluation of the airlock. I don't have the video, but I have a sequence of image. So we started with the suit to understand with all the collision to evaluate the airlock. So we interact with the doors, we open it, we went outside, we did a sort of EVA, and we come back inside the airlock, and we reattached to the suit port. So this was like the evaluation of the airlock. For another experiment that we did of this interactive evaluation was the evaluation of the racks. So try to move those racks and understand if this type of operation was useful or not. And so what we did was like using Unreal, we tried to did on ourselves this type of operation in the virtual reality. So what we did was just try to have a sort of interaction with those racks on the rails to evaluate this type of design choice. So after that, the idea is how to go to the next level. Well, to provide more immersion, you should design, for example, for the airlock or the racks, you should design a low fidelity mockup and, for example, interact with the virtual reality using mixed reality. So you have like a visualization with the VR headset, but you have also the physical touch of the elements that you are moving, for example. Like, for example, for the airlock, it could be like just opening the hatch, a sort of evaluation. So we already did this sort of simulation and mixed reality evaluation here. Like, for example, this with this tool that the astronauts use during the VA. You see on the top, this is the tracker that match the digital twin that you model on Unreal to the physical twin that you are using on your hand. So obviously here at SIXA, we are using those evaluation for lunar habitats, but also, as I said, for evaluation, for example, of assets like rovers. So this is like the evaluation of a lunar terrain vehicle that a student for her master thesis did here. I always did an analog mission in Lunares in Poland where I was commander, and I used this sort of framework to evaluate EVA operation and IVA operations. So this was my crew, and our official engineer of our crew was a Mexican from City of Mexico, and he is a really good friend of mine. And also here you can see the evaluation that we did using the VR headset for EVA operation and IVA operation. And so that we did like for 14 days of isolation mission inside the Lunar Research Base, 14 days of experiment mixing IVA and IVA. And there is also a paper that we presented at ESC about this experiment that I performed in Lunares. Last year, we also did the Moonshot. That was a workshop in collaboration with the Architectural Association School of London. So the idea was like to use Blender, Houdini, and Unity and Unreal and iterate this sort of software to obtain a fast outcome for doing a space architecture project in a really few days. So we did a really big project in 7 days. This is like some renders of the project that we did in just 7 days. And this video is the final outcome that we obtained after 7 days from Blender, from Unreal. So this was like the idea was like to set this project in 100 years from here. So with the mature technology of 3D printing on the moon. So the idea was to have the capability of large scale 3D printing on the moon. So this is the landing pad and the blasting walls to avoid the sort of plume interaction once there is the landing. And also you see all the base that is on a real terrain modeled from the data from the Lunar Reconnaissance Orbiter, and the habitation modules are down on that protective shell, also that 3D printed. So this is another view of the base. So solar energy and nuclear energy to power this base. And is all the lunar terrain on the South Pole integrated in Unreal. And here you can see we use the kilopowers that obviously is a demo technology for the nuclear energy on the moon. Probably in the future will be more powerful reactors. And here another video to focus more on what is the shell that was modeled on Houdini, that is a procedural software that we did for create this sort of matching protection of our cluster, habitational cluster. And okay. Okay, this is another project. I will be finished soon, so we have time for Q&A. It's another project that we did. So we participated last year as SIXA to the NASA Big Challenge. And the proposal was to design an inflatable lunar infrastructure for the moon. So I'm sorry, but our face is covering, okay, the video. Okay, so how it works? Well, the idea was like to inflate in different steps. So we inflate the first part, we rise this mass. In this way, we can avoid the tilting of the tower due to the slope of the moon. We come back, we put back this big mass that obviously is the electronics, the battery that aliments what we have on the top. That could be different function, and we inflate step by step. What grant the not tilted expansion and inflation are all these cables that are going around those disks. So in this way, we can keep straighten the tower to his axis. On the top, we provided the idea to have a beacon as a landmark for orientation on the moon, but also solar panels for power generation, but also communications, and also possibly mirrors for deflect the solar light in shaded areas. Also for that, we have two papers and two interactive presentations that we presented on the ESC last year. And that's all, and now is a Q&A. I hope that I didn't bother you too much with my presentation. I hope it was interesting, and I'm here to listen your question now.
Well, thank you so much for your presentation. I think it was so amazing because that's the thing that we want to share with our students, because here in Mexico we don't
I'm
have
not
a lot
good,
of
sorry.
reference with that. So thank you for that. Also, I want to mention that here with us is the principal, the director of the Faculty of Architecture in our university. So the name is Javier. I don't know if I would say this in Spanish. No sé, arquitecto, si quiere decir algunas palabras, o puede ser en inglés o en español si está por ahí. Si me escucha, no sé si me escucha porque creo que, a ver, creo que ya le activé su micrófono. ¿Me escucha? Well, he's trying to activate the microphone, so let me. Well, I think he's having problems. But well, he is here, so he was listening, and this is really important for us because we made something similar that to the project that you show. Let me share screen just for a couple minutes to show you. We made something similar. So if you can see, we make a graph also, and we develop a virtual environment to simulate that we are also in the space space station. But the first part of this contest was only in similar to the International Space Station, not in the moon. So it was in space just only.
Yeah, it's a microgravity testing.
Yeah. So the second of this contest, it will be in lunar surface. So we made this first, and in the second part, we want to do something similar like you are doing in Houston, just for just for show you this. But I don't know if somebody in the audience has some questions. You
Also,
can
if
put
you
in
have
the chat.
question about your project, because obviously I was running really fast about this project, but there are more things to say, but obviously the time is. The astronaut is supposed to be 1 month on the moon. Is there time to make regolith bricks on the moon? No, I assure no. Well, the problem about 3D printers that I was more optimistic about that, for example, in my.
Muchas felicidades
He's the principal.
por compartir conocimientos, ¿no?
¿Nos escucha, Doc? Arqui.
¿Estás acá? ¿Se oye?
Sí, ya lo escuchó.
Ah, ok. Bueno, yo soy Eduardo Bernal.
Ok.
Nos conocimos en algún momento porque en el laboratorio, ¿no?
Sí.
Y estaba viendo esto con Javier y bueno, decirles que es un proyecto súper interesante, que es una gran motivación, digo, aunque no comprendemos todo, ¿verdad? Porque de una complejidad muy grande, ¿no? Entendimos como todo el proceso en términos generales, ¿no? Y nos permite como comprender también la multiplicidad de personas que trabajan en proyectos como estos, ¿no? Desde los diseños de los trajes, las formas de aterrizaje, los sistemas de anclaje en esas superficies, etcétera, ¿no? Todos los sistemas de conexión, de interconexión, eh, toda la fabricación modular del proyecto que nos presentaron, pues fue realmente muy interesante. Y bueno, pues motiva para pensar que en algún momento, ¿no? El laboratorio en el que tú colaboras también, ¿no? Pueda paulatinamente incorporarse en proyectos como de esta naturaleza, ¿no? Y pues nada, que les agradecemos mucho, ¿no? Haber compartido este proyecto y dejarnos ver, pues, esta cosa tan interesante, ¿no?
Muchas gracias, muchas gracias. Well, he was saying that thank you for sharing your project because
Actually, if
we
you
are
want, I can say that
okay.
also. So I'm a professor in the architecture faculty, and we are really impressed by the work that you have shown us.
Thank you.
And it is really interesting, and it's a great motivation for um, uh, for us in the lab in the architecture school. And we hopefully we one day we can take part in a project like this, you know, or at least in a part of the project. Of course, it was really interesting to know all the complexity of a project like that. No, I was telling him that all the people, all the team that you have reunited to work in this project, all these persons who are in charge to develop these landing systems, the clothes, the human movements, and all that stuff, no? So thank you so much. It's a great motivation in the architecture school, no? Thank you
Thank
so
you very
much,
much.
Akatsin, that you, have shared this conversation with us. Thank you so much, and congratulations.
Thank you very much. I appreciate it. But I hope to be a sort of inspiration with someone because, someone inspired me before. So obviously, it's a sort of legacy that I'm happy also to participate in events like this, to talk with students, also to collaborate with students sometimes. So there is always something to learn to everyone, or. And I also think that, yeah, it's really complex, and sometimes I'm harsh a little bit when I see some sort of projects because it's something that you have to design for space. So obviously, it's really important the architectural part and what we know about Earth. But obviously, is equally important to understand the space system because we are thinking about a world that is on space and works differently. We have so many constraints that change every time in different type of situation. We have a lot of limitations that sometimes open also. A possibility of design when you have so many constraints, or to invent something new, to invent something that is more efficient. But yeah, just a little bit, just a little comment about that. I think that need to be important also the known of space systems when you're designing this part of when you want to approach this sort of design. But thank you very much. And I would like to answer also to Miguel that asked if the astronaut is supposed to be 1 month on the moon, if there is time to make regolith bricks on the moon. Well, I was saying, obviously the astronaut will stay on the moon not for 1 month as a first mission. So it will be a sort of evolution of the time during different type of missions. So you will start probably with 7 days, will extend 14 days. So it will be a sort of progression. You need probably to do missions before without astronaut to be sure that the habitat survive, that every system works properly. And no, there is probably time to test the technology in 1 month. So maybe test if you can print something on the moon, but you have really big constraints about the 3D printing on the moon because you have times of, for example, there are really strange temperature, extreme temperatures on the moon. So you can go almost close to the 0 Kelvin in the permanent shadow area and more than 100 degrees in the lit area. So obviously you have a big delta T of temperature, and this can change a lot how the technology behave now, the 3D printing on the moon. Also, there are so different type of 3D printing technology. I was using the binder jetting that assume that you need to deliver a sort of binder from Earth, and you use the rest that you get from the lunar regolith. But there are other technologies like solar sintering, microwave sintering, but if you are thinking to, for example, use a sort of solar sintering where you want to melt the regolith and attach layer by layer, there is a problem also how the time for curing the material without to crack it. So if you want to maintain the property of compression resistance you have to respect a sort of timing. So for big, huge structures like the sort of landing site that I proposed in that video, you could require maybe years, like 10, 50 years to build with many robots, something like this. So I like the idea that there are also big grants for NASA, for companies in US trying to develop this technology, because we need to test it as soon as possible, because we need to have more data for how works this type of technology on the lunar surface. Because for what we know now, there are not so wonderful mechanical properties, and also the time of printing could be a problem. Also, I don't know, you need to understand that you need to create many layers, and you need to create a way to protect for radiation, and probably just that dimension is not enough also if 1 meter to protect your habitats for radiation. You can mitigate it, but could be not enough. Let's see another question. The white membrane of elastic layer that cover the work area, when it expands or reacts, what density does it acquire when it is under tension? It can suffer crack when it is located in work areas. I see that there is a lot of free space. It is for reason, settings, air pressure. Well, I basically adapted a system that you can find many papers, and obviously it's a technology that is under development, and you can find a lot of answers about that from ILC Dover and the Serra Space that they are developing and blasting. Probably you saw YouTube this video for the live module. So they are creating a sort of, so this system is not just a membrane, but is composed by many layers. So there is a bladder layer inside that is meant to keep the pressure, because obviously everything that you design in space is a pressurized module. So you have pressure from the interior that expand to the exterior. That's the reason why you design everything with those rounded corners. Otherwise, you have a big difference of pressure and you risk failure points. That's one reason. So you have this bladder layer at the interior that contain the pressure, and obviously you have many layers outside that obviously are for the delta T of temperature. So you have the multi-layer insulation, and also you have the layers that has to emulate the Whipple shield. So a sort of stratified layer of Nexel, of Kevlar. There are many type of Whipple shield that you can create from, where the idea is like with the first layer, you break the meteoroids that impact to your modules. So after you have more smaller particles that get absorbed from the other layers. So in this way, you avoid that the meteoroid create a hole in the bladder layer. So you avoid the failure point and the blast of the pressurized module. And yeah, maybe in our renders, for example, in the horizontal type 2, there are a lot of free space because it's not so deeply developed. The interior of that module was more, we were more focused on the surface vertical habitat, and is not optimized. It was a really preliminary design of those modules. I don't know if I answered enough to your question.
I think yes. I was wondering about the system that you choose for the how can I say that, the how can I say that in English, the ecological system.
Oh, the
El-
ECLS, the
yeah,
device.
the NASA
Yeah,
ecological system that is
yeah.
a system closed system.
Yeah, well, basically was one of the requirements from the Marshall Space Flight Center to start with an open loop ecosystem, and the idea was like in the late phase to reach a regenerative ecosystem. We didn't develop the ecosystem because just for develop a small part of the ecosystem, maybe you require 2 degrees in engineering because obviously you are treating the air, you are treating the liquids. Is a system that is so really complicated, and so there are a lot of expertise that work on that. So we just took the system. We studied the system and we tried to readapt the one used in the ISS that now is a known state of the art. So we applied to the lunar habitat, and our idea is like, in particular for the early phases, could be just one, but after you need to provide a secondary smaller one at least for each vertical surface habitat, because obviously in space you always need redundancies, and also you can't you need also contingency plans. So if something fails, you need a plan B to save the astronaut, because it's the first thing when you start to explore the space is like the survivability of the astronauts. We are not anymore in the 60s with the race from US and Russia. And so it's now the most important thing is in every space mission is survivability of astronauts. And also is really important to do the next mission, because the public opinion now is like something that we know after the shuttle disasters. So it's like something that we don't want to repeat, in particular on the moon.
Sure. I think we have another question. I think it will be the last one.
Yeah.
Want to
How
answer?
are the effects of microgravity and space radiation on the physical and mental well-being of astronauts considered when designing habitable spaces in space? Well, the effect of microgravity, we have a really good know-how from the International Space Station. What we know less is the effects of the partial gravity, like Moon, that is the 6 times less than Earth, and like Mars, that is basically 1/3. So for microgravity, we know what changed a lot, and I can say something about that because I did an analog mission of 14 days in completely isolation, also from socials, with dry food, with a nuclear system inside the base. So what I know is after 14 days is a big game changing. And I saw that after the end of the 14 days of mission that I start to be really in bad mood. And so the psychological aspect is something that is really important in those type of mission. And you need to create a good environment inside the base for the astronauts, because the mental aspect can create or jeopardize the entire mission if someone has a breakdown or something like this. We already have experience like this, for example, for the space station Skylab, when for a while the astronauts start to switch off the mission control because they were like, the schedule, for example, was changed after the experience of the Skylab space station. On the ISS, they have now an amount of free space, just private space for the astronaut. That is the most important part because you have a schedule that is really tight, and so you need your private space. You need also moments where you don't have the others, your crew around you. Sometimes you want just to be alone, at least for a part of the day. You don't want to hear the others. You don't want to smell the others. You don't want to interact with others for a part. If you have a long-term mission and you always have this type of situation, privacy could be also a huge problem. And we see that, for example, for the mission on Antarctica, we have many bases there, and sometimes mission on the bases on Antarctica are more challenging their basis on the ESS because we have problems that, for example, with the C-130, the big planes where we deliver people on Antarctica, there are periods of the year where you can fly there. So you have long period of mission, like 3 months sometimes. And so the psychological aspect is something that we need to consider, not maybe so much for short-term mission, because we know we already did the Apollo mission and other type of missions, but for when we extend after 14 days or 1 month or probably more, is something that we need to consider. For the radiation, I don't think that is like a mental problem, but it's like a problem of life. If you are not protected from radiation and you are affected from a solar flare, for example, you are not protected from the geomagnetic field, terrestrial geomagnetic field. So you have like more than 50 times the radiation that you have on, for example, on the ISS, and so it's really is a big problem if something like that happens. Obviously, the risk is pretty low for short-term mission, but when you extend also that the period of the mission is something that you need to consider to protect astronauts. Hydrogen materials are the best. So also polymers enriched with hydrogen are the best element that can protect for many type of radiation. Also with the not so big layer of, you can have less. If you use loose regolith, there are some studies that you need 7 meters. So that is something that you need to consider.
Well, thank you so much for answering the questions, Corrado. We are really happy that you are here today, and hopefully you can still helping us to develop some new projects here in the faculty. We have a virtual reality laboratory. We have around, I don't know, 15 computers dedicated to virtual reality, and we have several 3D printers too. So maybe we can discuss later how we can collaborate with something similar, like to involve more students and to be, I don't know, collaborating between some, maybe Italy, United States, and Mexico. And
Yeah, sure.
I think that would be awesome.
Yeah. We can do in the future. We can decide a day to have a call and we can discuss
For
later
sure.
about that for sure.
Well, thank you so much for being here. I will send you an email with some details about the to be a judge for the last part of the contest. So I will sending some details later, and well, thank you so much for being here today.
Thank you very much for your invitation. I hope that was useful. Thank you.
Well, see you soon. Bye bye.
Thank you. Bye
Gracias a
bye.
todos por estar acá. Gracias. Bye bye.
Gracias. Bye bye.